Welcome back, everyone. In the last threads video, we covered a lot of ground. Fields, group theories, Lagrangians, mass terms, massless terms, symmetry breaking, massless bosons, all that good stuff. The common thread amongst all of them was this underlying idea of symmetry and gauge theory. It's essential now to dive deeper into gauge theory and gauge transformations because we keep seeing it appear everywhere. And to do this, I suggest that we start with this excellent thread by Martin Bauer, which is linked in the description if you want to read it yourself. But what Martin does is start off with giving us three perspectives on gauge theory, stating that one, qualitatively, at the core of gauge theory is charge conservation, which we saw in come into a big play in Griffith's Introduction to Electrodynamics. I can't remember which chapter, I want to say 6 in there as well. But we talked about conservation, or chapter 8, now that it's coming back to me. But we talked about charge conservation and how that was a local charge conservation. Global charge conservation, okay, we can kind of see a picture there where all charges have to be the same, something like that. But what we are interested in is the local and locality of those things. So go refresh on Griffiths, and if we need to, we can have a nice comment section. But we have to realize that gauge theories and all those other things that we saw from Hassan's video with the standard model are all about localizing things within a small space of all possible. So keep that in mind. And to which Martin now continues, a gauge symmetry makes sure that all observers agree about the presence of conserved charges. For this to work, we need a massless mediator, but why? And, for the case of electromagnetic fields and interactions, that mediator is the photon, which we've seen time and time again. So, let's continue on this journey and see what else this thread has. But as a quick interlude, for my subscribers, I posted a new PDF on gauge transformations and the minimal coupling rule, which is the Lorentz force law in quantum mechanics. You can find the link in the description, but because this topic keeps appearing everywhere, from chapter 10 in Griffith's Introduction to Electrodynamics to 4 and 6 of Griffith-Schroeder's Introduction to Quantum Mechanics, the necessity to really cement an understanding of this topic runs deep. But enough with my rambling, let's get back to this thread. So, Martin then continues on, and I really love this sequence that he has because it shows us why this is the case, and it's very important to us to have this intuitive understanding moving at things that we can't necessarily see or feel like we can with the electric and magnetic fields. So, consider an electric charge and two observers. Observer 1 right here, is at rest with respect to the charge, whereas observer 2 moves away. Both know about the presence of the charge because of the electric field. So the field is something that is observable, it's something that we can incorporate, it's something that we can feel, right? We can measure it. Okay, so the scenario at rest with the charged particle and moving, but we can still feel it regardless of if you're moving or at rest. To which this continues. Now the charge is removed. This information reaches both observers with the speed of light. This doesn't imply that it reaches both at the same respective time, but whenever they communicate, they would agree that the charge is gone. Okay? So this makes sense. We find out that it's gone because the electric field itself is now not measurable. Okay? But let's take a step back and kind of work in a contradictory manner, or let's work in a frame to where we can lead to a contradiction, like we do in math proofs, and see why this can't really be, why this has to be the case, and why the other can't be. So he says, let us imagine the information that the charge is gone would move much slower, so slow that observer 2 moves faster. In that case, the information that the charge is gone reaches observer 1, but never makes it to observer 2. Again, the information will reach the non-moving person, or observer 1, but will never reach observer 2 because the observer is moving faster than the signal itself. Okay, sounds a little weird, but let's hear it out. So from that, what we could say is that observer 1 could now send a message to observer 2 with the speed of light, informing her that the charge is gone. Observer 2 would disagree as she still measures the electric field at the original position because the signal that is vanished is still on its way to her and will never reach her. So the signal is still propagating to her, but the other observer already witnesses the fact that the charge is gone and tells her. So she's like, how is it gone, but I'm still feeling something? So, to which this is the contradiction that we will see now. So, the only way to avoid such a situation is if the charge itself lets all observers know about its location using a signal propagating with the speed of light. Okay, that's the upper bound of the speed of the universe and all those other things that Einstein postulated with general relativity. But only massless particles move at the speed of light. Remember how we had the rest mass that we had for particles, and that would only occur if the particle was, quote, massless. Things like the photon, energy, c squared, that relationship, that famous formula, that all works for, quote, massless things like the photon. Okay, clearly there's a lot more theory behind it, but as you see in this GIF diagram, the fact that this charge is moving, it has a propagating information wave all throughout here that tells you, hey, look, I'm moving, be aware. And you might feel the difference in field, and that field tells you the movement. This is the radiation field that Abraham, I believe, I can't remember the names, but chapter 11 of Griffith's introduction talked all about this stuff. Very, very important for us. So moving forward then, what can we do? In the case of electric charges, this massless particle is the photon, which, by the way, I just saw someone post something about the fact that the photon was actually called this first by a chemist, and he thought that the light itself was an atom or atomic style structure, something independent. And it was actually a famous chemist because you've probably seen these diagrams before. It was actually of Gilbert Lewis from Lewis diagrams, things like that. How cool is that? So as you see, all these fields of physics or science in general kind of work together in the weirdest ways possible. That's why open collaboration and discussion is so valuable to us in trying to unearth and gain an insight onto what the universe is actually telling us and how we can put that in words that we can comprehend. Very cool stuff. But the gauge boson, or excuse me, but the photon is the gauge boson of the electromagnetic gauge theory. Again, all of this stuff keeps coming back to gauge theory, gauge bosons, gauge. Why? Well, it is the photon's job to update every observer about the presence and positions of electric fields. And we saw in Hassan's video how these gauge symmetry breakings, these gauge symmetries locally, all that other stuff, that led to massless bosons, as you see here in the description of the picture. Massless gauge bosons tell you about everything else in that specific field. For the electric and magnetic fields, we have, or for the electric field, we have charge conservation. In magnetics, we have the electromagnetic force vector, which is the current potential, the vector current potential. But nonetheless, these things all come into fruition. And as you see, you get one from the other and the other from the one. Very cool and very much needed when we go into higher theories. All right, so moving on then. For the second perspective, we need to consider what physicists like to call the gauge symmetry, and that is a redundancy. Why is that? Well, in four-dimensional spacetime, gauge bosons, like the photon, are represented by four vectors, which, again, we've seen a little bit of in the Griffith stuff from E and M, but these four vectors are very much what we need to continue. You probably saw a lot of this notation from the Hassan video. These all tell us that we're covariant, contravariant, but we're all in the form of four vectors. And if you remember, the electromagnetic four vector potential was the scalar potential and the vector potential for the magnetic field. Local charge conservation was stated as the divergence or the gradient 4 vector, something like that, of the vector 4 vector, the current 4 vector, and that is why everything in the case of 4 vectors works so well. Time and position coordinates, scalar and some other vector coordinates, it all works very well in a 4 vector. But moving forward, Martin continues on by saying, if we look at the wave picture for the photon, it is clear that it only has two possible polarizations. It can only ever oscillate perpendicular to the direction of travel. Okay, so clearly k is the propagation vector, so this is the direction of propagation. But notice here how we have the electromagnetic wave where we have vertical and horizontal oscillations, but we're still traveling forward. And Martin does a great thing in the next thread by comparing it to sound. And it's very important because he states here that, sound waves, which oscillate in the direction of travel, can't ever do this. If a photon did that, it would sometimes move faster and sometimes move slower. But that would not work in the theory because photons have to move constantly at the speed of light. Very important. We see here that the propagation vector is radial, and we see that sometimes the atoms move faster, sometimes they move slower. Very, very important. Meanwhile, that propagation vector on the light was moving in the same speed in the propagation direction, but the oscillations were occurring mutually orthogonal. And he gives a great example of why this is cool. So, the two polarizations of a photon are also the reason why 3D glasses work. Although they are usually used circularly polarized light so that you can tilt your head without going dizzy, we see that we have a polarization filter here, polarization filter there, so we get what looks like a 2D image, or excuse me, separate images, but we're processing them in the same time. Very cool. I haven't seen a 3D movie in forever, but they were a lot of fun as a kid. The point is, the photon is a 4 vector, but only two basis vectors are needed to fully describe it. Weird. Very cool. But that is the redundancy. And what they say here, or what Martin continues to say, is that the other degrees of freedom are redundant. Okay? And now, in the last video, I believe, we talked about how degrees of freedom propped up in the forming of the standard model Lagrangian, things like that. Here's a little bit of how the degrees of freedom work. And there's a couple other Reddit threads, which I definitely will link, that describe things like how you can move the location of the origin in classical mechanics, Newtonian mechanics, but the physics doesn't change. So that is a degree of freedom that you can have, things like that. So it's worth trying to dig into all these terms and seeing what they mean instead of just rebuttaling them because you heard it somewhere. So they have some great intuition on those Reddit threads and Reddit pages. Definitely check them out if you're interested. But Martin extrapolates this and says, same is true for all massless particles. The metric tensor has 10 entries. Whew. Yet gravitons only have 2 polarizations. Every observer can choose the bases for these polarization vectors differently. Makes no difference for the physics. The choice is the freedom to pick the gauge, or pick a gauge. Similarly, the wave function of a charged particle is only defined up to an arbitrary but related phase. And this is where we get perspective 3. Now, what he goes into is slightly different, and I don't know if he was just having fun or worked on a project like this, but it's a great illustration to me and will be for, I'm sure, several others. Mathematicians make everything needlessly complicated, so instead of saying every observer can pick a phase and a corresponding polarization vectors, they say at every space-time point, there is an internal space corresponding to this choice of phase. Yeah, so as you see, language can sometimes conflate what we're actually trying to describe, or we might not even have, quote, the jargon or language to fully describe what we are trying to state, and that's why it is very difficult to deal in all these higher level theories and higher level new or relatively new topics because we might be talking past each other, or some books might be difficult because they're talking in a very particular sense of language. That is why having more discussions, more perspectives can help in gaining you the insight that you need, regardless of how it necessarily gets there. And as you see here, we have e to the I theta, which is a product or a function, not a product, of x, the vector, and t, and you can see that this polarizes it, but we're still spaced out evenly in the xt space, so that's pretty cool. And then he continues on this thought train by saying, they call this construction a principal fiber bundle. And if you've heard of other things or have seen Martin and Eric Weinstein's back and forth on X/Twitter, you see how Eric is a big proponent of the principal fiber bundle. In fact, you probably have heard of him on Joe Rogan talking about that. Very cool stuff, but definitely takes a couple more math classes to get up to that. But we can talk about the ideas like Martin proposes here. And so the fibers are the internal spaces, space-time, and the base space. Picking a phase for the charged particle wave function at every space-time point corresponds to tracing out a path, or a section, in the internal space. So we have the section here, we're tracing it out, pretty cool diagram, very much a helpful one. And we see that here on the principal bundle, oops, we see that we're still evenly spaced, and it's really cool construction that he put this thread together. But moving forward, we see that for mathematicians, gauge freedom corresponds to the freedom to pick such a section. The photon polarization vectors corresponding to this choice of phase need to be chosen at each point. This allows to obtain the same physical results everywhere. Okay, very cool stuff, very important. But the next thing in this thread is something that you might just want to screenshot or capture or go take the picture from his Twitter or X post, whatever you want to call it, because it definitely pops up in a lot of other physics books. And let's see what that is. The photon is necessary to compare results at different points in spacetime and different choices of phases. Mathematicians call such an object a connection on the fiber bundle. And if you listen to Sean Carroll like I have, or a couple other, quantum field theorists, they talk about the theory of connection, connectors, all these other things. The connection is what makes all of this stuff come together in a sense. And, still diving into it myself, there's still a lot to be understood. But the picture here tells us that, look, we have the point X, point Y, we're moving through, we see everything. It still corresponds to another space, from this space to that space, and it tells us everything we need to know about the different spaces and the choice of phase, which I find very, very cool and very enlightening. However, the math is definitely difficult at first until you start, of course, just dealing and, trying these theories out, proving them, doing exercises, things like that. Why do we care so much? Well, Martin then gives this nice example, um, where we get to see, with mathematical description is the most powerful in generalizing the concept to higher dimensional bundles and fibers in the curved base space. And why this all comes together is that some of these generalizations have physical meaning. For example, he gives the Yang-Mills theories like in QCD, and others just lead to pretty pictures, which he quotes here, or shares here. And yeah, it is an overwhelmingly beautiful theory, picture base, all that stuff. But just imagine that these theories continue to compound on one another, and we don't know why. But then when we go looking and prodding, we can see the construction of physics that we're trying to write out in a language that was already corresponding to something that math had kind of used in just the abstraction land. So these two things are more closely related than maybe we had thought previously, but nonetheless, this stuff is fascinating, and more of these examples keep popping up, and we see that the importance of them at every level of increasing difficulty, we integrate more and more of the gauge theories, and we see them coming in and out um, in these textbooks and more relevancy. So I could ramble on more, but I think the concept of the gauge tells us about the local charge conservation very well, and that we see from there the only thing that could do that is mediated by a massless particle, which, referencing again Hassan's thread, those massless particles give us information about the fields themselves, and we need to know more about this. So I'll post more of these because the feedback was good and it's a lot of fun. But, that's it for this one. As always, stay curious.